far-field imaging, particularly for applications such as remote sensing, astronomical observation, and surveillance, is often limited by the diffraction limit of the imaging system's aperture. According to the diffraction theory, the resolution of an imaging system is directly related to the size of the aperture and the wavelength of illumination source. In practical terms, the diffraction theory means that for distant objects, the ability to resolve details is fundamentally constrained by the physical characteristics of the system. Fourier tychographic microscopy (FPM) is a powerful phase retrieval method that iteratively combines real and reciprocal space information. Based on Fourier optics and tychography, FPM illuminates a sample from different angles using a LED array. This enables the capture of diverse spatial frequencies, facilitating simultaneous phase recovery and aperture synthesis. Its simple hardware and superior imaging capabilities make FPM widely applicable in biomedical and pathological studies. By replacing the LED array with aperture scanning, in the far-field detection, macroscopic Fourier tychography serves as a non-interferometric aperture synthesis imaging method that enhances the resolution of far-field targets. Importantly, macroscopic FP addresses the inherent trade-off between the imaging distance and field of view, making new pathology for far-field applications. Despite their physical differences, FPM and macroscopic FP face common challenges in phase retrieval techniques. Both FPM and macroscopic FP rely on data redundancy for stable iterative convergence. The overlapping ratio is achieved through dense illumination and scanning, resulting in a significant enhancement in efficiency despite the requirement for numerous image acquisitions. Multiplexing has proven effective in computational imaging by decoupling individual images for information extraction. In FPM, multiplexing illumination reduces image acquisition without sacrificing data redundancy. Color cameras enable direct RGB channel separation but face photon efficiency and filter-induced downsampling issues. In our approach, we utilize a camera array for parallel acquisition to avoid the issue of insufficient temporal resolution brought about by aperture scanning. By employing a single exposure method, we address the far-field imaging issues of moving targets or dynamic scenes, achieving high temporal resolution macroscopic FP. Our work, snapshot macroscopic Fourier tychography, far-field synthetic aperture imaging via illumination multiplexing and camera array acquisition, has been published in the Advanced Imaging Journal and was selected as the cover article for the inaugural issue. It has also become the most downloaded paper in the journal to date. By arranging multiple cameras in an array, we can capture images from multiple subapertures in parallel, instead of sequentially as in traditional aperture scanning methods. This parallelization is essential for enhancing the system's temporal resolution, making it possible to capture real-time images of dynamic scenes. To maximize the resolution gains, we employed an illumination multiplexing approach using mixed RGB wavelength source. The different wavelength channels are designed to overlap in the Fourier domain, allowing us to extract more detailed information from the captured data. The computational backbone of our approach is a refined Fourier tychography algorithm that can handle the complex relationships between subaperture positions and spectrum shifts. By accounting for the nonlinear dependencies between these factors, our algorithm accurately reconstructs both phase and amplitude information from the captured data, even when dealing with far-field conditions. In our experiments, we demonstrated the effectiveness of IMSSI by imaging a moving object at a distance of 2 meters. For instance, we demonstrated the capability to perform real-time super-resolution imaging at 30 frames per second, capturing detailed images of objects in motion. The capability of snapshot imaging is particularly important for applications like remote sensing and surveillance, where both speed and detail are crucial. It can be observed that the original low-resolution image is too coarse to discern meaningful details, while the result obtained through cumulative averaging of subimages only displays partial contours. In contrast, the proposed IMSS-SI yields optimal super-resolution reconstruction, and the imaging SNR is further enhanced through total variation, guided filtering denoising processing. The potential applications for IMSS-SI are vast and varied. In remote sensing, the ability to capture high-resolution images of the Earth's surface in real time can provide valuable data for environmental monitoring, disaster response, and resource management. In astronomy, the technique can be used to observe celestial bodies with unprecedented detail, even as they move across the sky. In defense and surveillance, the imaging ability to track moving targets with high resolution and in real time offers significant advantages for situational awareness and threat detection. Our research contributes to the advancement of Fourier tychography and provides a foundation for the next generation of high-resolution, real-time imaging systems. We are actively advancing the implementation of IMSS-SI technology into the realm of remote sensing for far-field imaging.